If we look at influenza virus in itself, it's got an incubation period of around about 2 days. Symptoms tend to be a marked fever, headache, photophobia, shivering, dry cough, tiredness, and a dry tickly throat. And that fever can last anywhere from 3 days all the way up to a week or 10 days if you have man flu. Not that I would ever get man flu, of course. You can get secondary bacterial infections, such as Staph aureus, and that's a common secondary bacterial infection. And theoretically, you can diagnose it, so you can detect the antigen, so that's part of a protein, if you like. So influenza antigen can be detected in nasopharyngeal aspirates and throat washings. You can isolate it from nose and throat swabs. So there are 3 main subtypes of influenza virus. There's influenza A, and there are many different serotypes of influenza A. For example, H1N1 or H3N2. And this virus, so influenza A, undergoes both antigenic shift and antigenic drift. And I'll talk about what those two are in a moment. But this is the reason why we can have such big changes in influenza virus, influenza A virus in particular, but also why it can be so pathogenic at times. So birds are a natural host, and the virus can be transmitted to other species, such as domestic poultry, and then obviously onto humans. And this is the most virulent influenza type and causes the most severe disease. We've then got influenza B. There's only one serotype there, so there's no H1N1, HN2, etc., etc. It's just influenza B. Almost exclusively infects humans, and it undergoes antigenic drift only. And it undergoes that antigenic drift and it mutates about 2 or 3 times slower than influenza A. And it's also less severe than influenza A. And finally, we've got influenza C. There's only one serotype here, again, influenza C. It's relatively stable. It mainly infects humans, often children, and it only causes mild disease in children. And it undergoes antigenic drift only. So what do I mean when I'm talking about influenza virus antigenic drift and shift? Well, influenza A virus undergoes both antigenic shift and antigenic drift. It can infect other species, such as birds and pigs, unlike influenza B and C, which only infect humans. And what happens is 2 strains, for example, from a bird and from a human, if they co-infect a cell, for example, in a pig, you get random packaging of the genetic material, in this case, from the bird and from the human, to create a new viral strain with major modifications. So in this example, the pig is the mixing bowl, and it's got a mixing of an avian influenza with a human influenza to come out with a human influenza, which has got something that we haven't, as humans, seen very much before, or seen at all. So there are major, major changes. And it's thought that the pig is actually thought to be the mixing bowl, where you get this reassortment going on. And it's most likely to occur in places such as China, where animals and humans live in close proximity. There are times when you have more than just 2 mixing together. So in this case that I've shown you, you've got the avian and the human mixing with the pig to come out with a human. But actually, sometimes the pigs are also infected with the swine flu, swine influenza, and you get a triple mix. And actually, in one pandemic many, many years ago, there was a mix of 4. There was an Asian swine flu that mixed with a regular swine flu and an avian and a human to give a new human, if that makes sense. So huge modifications can potentially go on, to which we have very little immunity because we haven't seen those viral proteins before. And of course, that can therefore go on to lead to extensive pandemics about every 10 to 40 years. But of course, as that immunity starts to build to that new subtype, further epidemics and pandemics are more limited. But what is an epidemic and what is a pandemic? So I just want you to quickly define epidemic and pandemic. So an epidemic is where an infection infects many people at the same time. So in other words, more people are affected than would be expected. Whereas a pandemic is basically an epidemic on a global scale. So we talked about antigenic shift, which is basically about the RNA of the influenza virus just being passed into new strains. So you're just mixing the RNA all over the place. Now, antigenic drift is just due to mutations in the virus itself. Okay, and like I said, When you have an influenza infection, that influenza replicates within your cells, in the lungs, and actually you get almost every virus that comes out is slightly different. Okay, so you're getting that antigenic drift happening a lot. But they're only very small changes. They might not affect the protein structure at all. They might have no difference, or it might just kill the virus off. Okay, but each one is slightly different. But because there aren't big changes, you very rarely get an epidemic. So that's why you only get the epidemics due to these new virus strains occurring every 2 to 3 years. And there is still partial immunity because of the cross-reacting antibody induced by previous infections. They're generally not big changes. And of course, there's a vaccine available. And the vaccine for 2018, most people now have the quadrivalent vaccine as opposed to the trivalent vaccine. And as you can see from this, it's just showing you have 2 influenza A's and you have 2 influenza B's. And really, when a sample of virus is taken and grown in culture, it is called an isolate. And the particular lab serial number or isolate codes, which is quite arbitrary, but specific to each lab, the animal the isolate was taken from, its location and the year all become part of the strain designation. So hence, influenza A was isolated in Michigan with an isolate code 45, don't worry too much about that. And the year was 2015, and because it's influenza A, it was H1N1. And the second one is influenza A, isolated in Singapore, don't worry about where from, 2016, H3N2. And then you've got influenza B, Brisbane, 2008, and Phuket, 2013. So you can start to see how they're actually designated. So there have been avian influenza outbreaks, and you can understand why now, because we've got that big mixing bowl going on. And there was a recent outbreak of avian influenza because of a strain of H5N1 influenza virus. And when we talk about H1N1, H3N2, H5N1, it's all down to the proteins on the surface of the virus. So H just stands for hemagglutinin, and it's number 5, and N stands for neuraminidase, and this one is number 1. So they're just slightly different proteins. So you can have a H3 there, an N2, whatever it might be. And this bird virus infects humans without undergoing a recombination event in some other animal. In other words, there was a species jump to humans because of drift. Now, this is rare. Normally, the species jump occurs because of shift, antigenic shift, not because of antigenic drift. Now, in this case, the fatality was about 60% in humans. Luckily, as the virus wasn't readily spread from birds to humans or from one human to another, there weren't a huge number of people actually killed. However, it could theoretically mutate or undergo reassortment with another human influenza whilst remaining as virulent, because remember, 60% fatality is quite virulent. So, how do we actually get a pandemic starting in the first place? What are the 3 conditions that need to be met? Well, you need to have a new influenza A subtype emerges to which we have no or very limited immunity. And that was the case with this H5N1 avian flu. The virus can infect humans, resulting in serious illness. This was also the case with H5N1, remember, with 60% fatality. Human-to-human transmission is efficient. Fortunately, with this one, this was not the case. It was very, very inefficient at human-to-human transmission. Therefore, we really did not get any pandemics or epidemics. But theoretically, you could do, okay, if it was to reassort with another virus that spread a lot better. So there have been some serious past influenza pandemics. So the earliest one that lots of people refer to is 1918 H1N1, which is Spanish influenza, which killed upwards of 40 million people. You've then got some other ones. You've got the Asian flu, the Hong Kong flu. You've got re-emergence of the Spanish flu in 1977. You've got swine flu, which kicked off in 2009. And then you've got the seasonal flu, which remember is often H1N1, H3N2 with your Bs. And that kills around about 500,000 people every year. So it's still a significant killer. Death rates, of course, tend to be a lot lower now as antibiotics are available, which are helping to prevent secondary infections. So remember, you get influenza and then you might well get a secondary bacterial infection. But there was some controversy because a few years ago now, well, what's that, 14 years ago, the H1N1 genome was published in the magazine Science. And there was fears that this information could potentially be used for bioterrorism. It doesn't appear to be the case, but there were fears at the time when it was published. So really I want you to just do a little this is a comparison table, and I want you to think about what have you learned about influenza A, B and C? Which is the nastiest? So what's the illness severity? We can just put pluses in there. What's the animal reservoir? So where can it actually multiply? Do we have human pandemics? Do we have human epidemics? And what are the antigenic changes? Is it drift, shift, or both? Okay, so press pause and have a little bit of a think. What can you remember on these different types? So illness severity. Influenza A, lots of pluses, very nasty. B, oh, sorry, we're carrying on influenza A. So animal reservoir, yes. Human pandemics, yes. Human epidemics, yes. Antigenic changes, that's both drift, which is your mutations, and shift, where you're getting reassortment of genetic material. Influenza B, illness severity, a little bit nasty, but not too bad, but it is included in the vaccine, of course. Animal reservoir, no, only affects humans. Pandemics, no. Epidemics, yes, you do get more infections because of it, and you get these localized epidemics. Antigenic changes, just drift, so just random mutations. And there's much slower mutations than in influenza A. Finally, influenza C. Illness severity, it's fairly mild and mainly in children. Animal reservoir, no. Pandemics, no. Epidemics, very, very occasional. Antigenic changes, drift, but it's very stable, so it mutates quite slowly.